Okay, so last section we're going to look at this week is section 3.2. Okay, 3.2 is on, there's really three separate things in it. Two of them are kind of connected, but it's on continuity, the intermediate value theorem, and end behavior. So when we draw things on the calculator, and this is especially true for an older calculator, it assumes that what you're drawing should be connected. Okay, let me show you the graph of a function that you should not draw connected, and how an older calculator draws it. Ignore those little squares on the screen. Just look at the curve it's drawing. Okay, that's a picture of the graph of tangent. What it really should look like is this. That's what the graph should look like. The parts that kind of go from the top here down to the bottom, those shouldn't be connected. But on an older calculator, it doesn't understand that idea that the graph shouldn't be connected. On the newer one, it does. Okay, so just kind of a warning, if you use an older calculator to do some graphs, you might end up with these funny lines that shouldn't be here. Newer calculator, that's not a problem. All right, so I'm going to graph this, and this is one that something funny would happen on an older calculator, but I'm just going to do it on the newer one. And it's 1 divided by, put the x minus 3 in parentheses. Now, if you're going to divide by x minus 3, where is something funny going to happen because you're not allowed to plug in this number? Yep, Dave.
You can't plug in 3 for x.
You can't plug in 3, so if you get very close to 3 on the picture, something weird is going to happen as you start to get close to 3. And what ends up, do zoom 6. What ends up happening as you get really close to 3 is the graph goes all the way down to negative infinity, and then on the other side, it goes up to positive infinity. An older calculator is going to try to connect that. Now, if I asked you to draw that graph out, could you draw both parts of it without picking up whatever you're using to draw? Andrew? What do you think? If I asked you to draw that, could you draw that without lifting up what you're using to draw? No, right? You'd have to, right? Because it's two separate pieces. One, and now how are you going to get to the other piece without not lifting your pencil? So you've got to lift it and then do the second piece. All right, so the question as we draw some graphs here is, can you trace these without lifting your pencil? That one is no. Okay, let's try this one. The integer function. Okay, so the integer function is under math, number, int, and hit graph. Could I draw that without lifting my pencil? No, because there's breaks in it. Okay, so I can't do that either. How about this last one? X squared minus 2x plus 4. Yeah, what kind of graph is that going to be? Yeah, it's just a parabola. Okay, and if we know it's a parabola, fine, I won't sketch it. But it's just a U shape, so you can draw that without lifting your pencil. So this last graph, h of x, has something that the other two don't. Okay, it has a property that we'll mention right now. Anybody know what the property is? It's called continuity, or it's continuous. Okay, so the idea of a function being continuous on an interval, right, means that it is possible to trace between the start point and the end point of your interval without lifting your pencil. Okay, that's basically what it means to be continuous. Right, so if I had a graph like this, and let's call that 0, 1, 2, 3. And I said to you, give me an interval that you could trace between without lifting your pencil. Well, one interval, I mean, there's an infinite amount, but let's say from 0 to 2. There's 0. There's 2 on my graph, and I can definitely trace between 0 and 2. That's an interval without ever lifting my pencil. I could also trace between 0 and 3, or 1.5 and 1.7. Okay? There's a lot of intervals I could trace between without lifting my pencil. Okay, but that's the idea of what it means to be continuous. From the start to the end, you don't have to lift your pencil to draw it. Any questions on that idea? Okay, that's kind of an informal way to define continuity, to say you don't lift your pencil when you're drawing it. I'll give you something a little more specific after. But what it really means is there's no holes in the graph, there's no breaks in the graph, and there's no undefined values. Okay? I'm going to show you an example of each of those three things I just said soon. Okay, so I'll say them again. If something's not continuous, then it's discontinuous. Okay? The first two graphs I showed you on the last page were discontinuous because you had to lift your pencil to draw them. All right. So just because a graph is discontinuous at a certain spot doesn't mean it's discontinuous everywhere. You might be able to find a section, maybe a very small section of the graph that is connected. All right? So what we're going to do now is I'm going to give you a graph, and I want you to name two intervals where you can have a start and an end point and trace between them without lifting your pencil. And then two other intervals where if you tried to trace between your start and your end point, you would have to lift your pencil. Okay, so we're going to graph that and see what it looks like. Okay, so the graph is 1 divided by x. Now, obviously, in this one, you can't plug in 0 for x because you divide by 0. So something weird is happening as you get close to 0. All right, so let's start with naming an interval that's continuous. Can somebody give me a starting x value and an ending x value, where if I went along the graph at those points, I would never have to lift my pencil to trace between the 2 points you tell me? Yep, Colin?
2 and 4.
Sure, between 2 and 4. 2 is right here. 4 is right there. I could definitely trace between the 2 points they each said without lifting my pencil. So that's a continuous interval from 2 to 4. Now you can write it like this. You could say trace from 2 to 4 including the 2 and the 4. You could say like that. Trace between 2 and 4 not including the 2 and the 4. That doesn't really matter. Okay, that's like tracing from 2.001 to 3.99. It's almost the same thing. But let's just do something different than 2 to 4. Okay. Somebody give me a second interval on that graph that is continuous. Casey?
From 3 to infinity.
Sure, that's a different kind of interval. That's an unbounded interval that's continuous. You could trace where Casey just said from 3 to infinity without ever lifting your pencil. You'd never get to infinity, but you'd never lift your pencil as you're approaching it. So from 3 to infinity. Do you want to include 3 or not including 3? It doesn't really matter whether you trace from 3 or 3.00001. It's basically the same thing. So those are two intervals you could trace between. One's bounded, one's unbounded. That's fine. The directions didn't say. Right? Now, can somebody give me an interval that would be discontinuous? If I tried to trace between this value and this value, I couldn't do it without lifting my pencil. Yep?
2 to -4.
All right, I'm just going to write the small one first. So -4 to 2. I could not trace from here to there. That's -4 to 2. Can't do it. Basically, anytime you cross what number in this graph, you have a problem. 0. Anytime you try to go from a negative to a positive, for this graph, that's where the discontinuity is. So I'll just pick another negative and another positive. Again, it doesn't matter if it's an open or a closed. That doesn't really matter. You could give an unbounded interval. You could say -5 to infinity. You're definitely going to cross 0 if you try to go -5 to infinity. Okay? All right. So any questions on that one? All right. I'm going to skip that one. All right. So I said to you there's 3 different types of ways a function can be discontinuous. This one is an example of an undefined value. It's a divide by 0 problem. You cannot divide by 0. 1 divided by 0 is undefined. You can't do it. Okay, so that's an example where the function just isn't defined. Okay, so that can create a discontinuity or a point at which you pick up your pencil. Another type of discontinuity is a break. With a break, it's not that you have an undefined value, okay, like in the integer function. In the integer function, you can plug in anything you want for x. There is no restriction. Positive, negative, fraction, decimal, 0. You'll never get an undefined value in the integer function. But the way the function works, the way it rounds things off, it causes these jumps or these breaks in the graph. Okay, so a break is different than undefined. Undefined is a calculation mathematically you just can't do. A break is not that. Okay, it's just the graph just jumps because it's the way the function works. So any question on the difference between a break, which I'll put down there, or an undefined value? Okay, so to be continuous, no undefined values, no breaks, no holes in the graph. The first two are very obvious to see in a picture. The last one is impossible to see. You cannot see that a graph has a hole in it by looking at a picture. The only way to see that your graph has a hole in it is algebraically. Hey, let me graph that. I want you to tell me what you think it looks like. Okay, so in the top, put it in parentheses. X squared plus 3x plus 2 divided by x plus 2. And I'm going to do zoom 6. What does that graph look like? Linear. It looks linear. And if you keep zooming out, it's going to keep looking linear. It's not like we're zoomed in on a small section of a curve. It would look linear. But what value are you not allowed to plug in for x?
-2.
Yeah, -2. But it's not quite the same thing with the 1 divided by x. The 1 divided by x had that curve that went to negative infinity, and the other side went to positive infinity. You can't see that here. That's because there's a hole. If you try to go to -2 on your graph, it's like if I trace and then type in -2, For the y value, it doesn't put a number because there isn't one. It's an error. If I go just after negative 2, like negative 2.00001, that's fine. I get a y value. Okay, if I go just on the other side, negative 1.99999, that's fine. I just can't use negative 2. Okay, so it's a very, very small section that I can't use. And that's because there's a hole in the graph. I'm going to show you why. I think it'll be clear in 1 second. Okay, let's factor the top. How does the top factor? X squared plus 3x plus 2.
X plus 2, X plus 1.
It factors as x plus 2, x plus 1. And what happens is you have an x plus 2 in the top. You have an x plus 2 in the bottom. It's almost like they cancel out. And the graph that you're looking at is basically just that. In fact, if I type that in, x plus 1, you won't see a difference visually between the graph I had before and the graph I have now. Visually, there is no difference. But there's a small hole in the original graph. Okay, so small holes happen when you have a common factor in the top and in the bottom. So if I took the original and let's just mess up one thing in it so that it doesn't factor as x plus 2, x plus 1. Okay, let's make it x squared plus 3x plus 3. Now the top and the bottom don't have a common factor because that doesn't factor now. Okay, I messed it up. So when I graph it, it's going to look totally different. Okay, I get kind of that behavior that I had the first time, where all of a sudden you get a line that shoots up very high and the other one goes down very low. Okay, that's not a hole. It's an undefined value, but it's not a hole in the graph. Okay. So any question on the difference between an undefined value that goes up and down forever, an undefined value that's more like a hole, or a break? Those are the three things you have to avoid if you want to have a continuous function. Okay. Something about polynomials that's important is every polynomial is continuous. Okay. Whether it's a line, that's a polynomial. A parabola, it's a polynomial. Cubic, or we even got into like some W-shaped things yesterday. I can draw any type of polynomial without ever lifting my pencil. Always. And if you have a function that is basically continuous anywhere, not just between like 1 and 2 or between, say, 2 and 5 like we did before, but you could literally give me any starting value, any ending value, and it's always continuous, that's called a continuous function. So all polynomials are continuous functions. So what if I gave you a polynomial and asked you to find an interval where it was discontinuous? What would you say?
It's not possible.
It's not possible. It's impossible. There are no discontinuities in polynomials. Okay, so any questions on that idea? A continuous function. It's a function that is continuous. You never have to pick up your pencil anywhere in the entire thing. Okay. Okay, so that's the kind of the first thing. The second thing is going to tie in with continuity. It's called the intermediate value property. Let me give you kind of an example of how this works. Let's say you had water, like, in a pot on the stove. Stove's off, okay, and it's sitting there, and the water is like 70 degrees. Okay, it's like close to room temperature. And then you turn the stove on and you heat it up to boiling at 212. As the water goes from 70 degrees to 212 degrees, what temperatures does it go through in between? as it's heating up?
70 and above until 212.
Yeah, all of them, right? It goes through every single one of them. It goes to 72, 73, 74.6, 74.626. I mean, you might not be able to measure that with a thermometer that accurately, but the point is, if it starts at 70 and it goes to 212, it goes through every single number in between, because boiling is a continuous process. You can't go from 70 to 112. Like you can't do that. It's got to go through every temperature in between. Okay? Versus if I walk across this room, I don't have to walk on every single, like if there was a line I was walking on to the door, I don't walk on every single part of that line because I'm taking steps. So I might skip parts as I'm walking. Right? So that's the idea of this intermediate value property. If you are starting at some value, okay, call that 70 degrees, and you're ending at another value, call that boiling, you're going to have to go through every value in between. So maybe A and B, and if you want to kind of continue my example with boiling water, maybe A and B represent time. A is at 0 seconds before you start boiling. So at 0 seconds, you're at 70 degrees. The water's just sitting there. And then maybe it takes, I don't know, 500 seconds for your water to get all the way to the boiling. So in this case, B is 500. And at that point, your water's boiling. So what this is saying is that if you pick any interval between 0 and 500, you will be able to get a number in between.
Wait, why 500?
I just made up, maybe it takes 500 seconds for the water to get to boiling. Okay. So like if you said to me, am I going to hit 90 degrees at some point? Yep. And we could find where. Maybe around 30 seconds, your water's at 90 degrees. Okay? But the point is, you're going to hit every single temperature at some point between 0 seconds and 500 seconds. So any question on that idea? Okay, that's why it's called intermediate value, because intermediate means between. Okay? You hit every value between intermediate to two other values. All right, so let's try this. First of all, what shape is that if I draw it? 3x minus 4. It's what?
Is it just a line here?
Yeah, it's just a line. Just a line. What I want to do is I want to look at that line on the interval from negative 10 to positive 10. So if you were thinking on your graphing calculator, x min is negative 10, x max is positive 10. We're just focusing on that interval. The question, and we have to see first if this is even possible. And then if it is possible, we'll try to solve it. But what I want to check and see is, am I going to hit a y value of 15? Somewhere in that interval. Okay? A y value of 15. If I do, then I want you to tell me where. When x is 1, when x is 2, when x is 6.5, where do you hit 15? So what I'm going to do first is I'm going to plug in negative 10 for x, and I'm going to find my lowest y value in that interval. Because you might say, well, doesn't a line go on forever? Yes, it does. But just in that interval. Okay, let's start with that. Okay. What's 3 times negative 10?
Negative 30.
And then plus 4?
Negative 26.
Negative 26. So our y values are starting at negative 26. Oh yeah, thank you. Minus 4. Yeah.
So we negative 34.
So yeah, it would be negative 34. Thank you. So our y values are starting at negative 34. And they are going up to, now let's plug in the other number for x. 3 times 10 gives me 30 minus 4, 26. So my y values are starting at negative 34. They're going up to 26. Am I going to go through 15 at some point?
Yeah.
Think, if you count from negative 34 to 26 and you don't skip any numbers, are you going to hit 15? Yeah. So you will hit 15 on this interval somewhere. Now I want to know where. So where would I plug in the 15? I would plug it in right there. And I already can guarantee you my answer is between negative 10 and 10, somewhere. And it'll never hit more than once because this is a line. So it can't, lines don't curve back down. Okay. So 15 equals 3x minus 4. Add the 4. And my last step?
Divide by 3.
Yep, divide by 3. So when x is 19 thirds, or what's that, about 6 and a third, when x is roughly 6.3.
It's 6.3 repeating.
Yep, 6.3 repeating, which is definitely between negative 10 and 10. So we answered the question. Okay, so the algebra part of this isn't really hard. You're just plugging a number in for y and solving for x. It's just the idea I want you to think about is that continuity. You're going from negative 34 to 26, and you're never skipping any number in between. That's the idea I want you to get. Hey, any question on that? Okay, let's try this one. This one, I want you to basically prove that that graph is going to cross the x-axis somewhere between 0.25 and 0.75. Okay. I don't care where it crosses the x-axis. All I want you to do is prove to me that it does somewhere. So think about if you cross the x-axis. What does that mean? You're going from what kind of value to what kind of value?
Negative.
You've got to go from negative to positive. Okay? That's the only way you could ever cross 0. You go from a negative to a positive, or a positive to a negative. So let's check, first of all, the y value at the beginning of my interval. Let's hope that it's either negative or positive. And then let's check the y value at the end of my interval, and we'll hope it's the other one. And then if one of them is negative and one of them is positive, I'll explain from there. All right, so let's, I'm not using the graphing calculator to actually graph this. I'm just using it to speed up the calculation. So plus 2x minus 1. Now I'm just going to use my table. Let's plug in 0.25. Okay, you get negative 4.99. Negative 0.499. Okay, so we're at a negative. Let's check the y value at the end of the interval. 0.75. Okay, 0.737. So, on this interval, I started in the negatives, and I ended up in the positives. So what does that mean?
It crosses
It has to cross through 0, because what kind of function is that? Because I could say count by 2's. and never count the number 0. If I went -3, -1, 1. I was counting by 2s, and I just jumped over 0. I didn't go through it. I jumped it. But what kind of function is that? That we know because of this, it's not going to jump over 0. A polynomial, and polynomials are always continuous. That's a continuous function. Okay? So it cannot jump anything. If it wasn't continuous, then what I'm about to write down wouldn't apply. Okay? So let's write down, since our interval, how can we say it? Since our interval starts in the negative and ends up in the positive, and our graph is continuous. It's important to mention that. And what do we call it? F of x. F of x is continuous. Our graph must pass through 0. Now, where does it pass through 0? We don't know. We didn't find that. But we know it has to somewhere. Now, could it pass through 0 more than once? Sure. This is a graph that can take up to 4 turns. Maybe between 0.25 and 0.75, it looks like this. If you zoom in. Well, actually, it starts negative. So it starts in the negatives. Maybe it goes positive, negative, positive. Maybe it does something like that. I don't know if it crosses more than once, but if it's going to go negative to positive, it has to cross at least once. So we proved that there must be a 0 in that interval. Okay. Any questions on that one? All right. Okay, so last thing. Okay, end behavior. This is kind of separate. End behavior is basically what a graph looks like on the extreme ends of your function. So if you had something like this. End behavior doesn't care about what's happening there. It doesn't care what's happening in the middle. It basically says, if you look at the left side, what's happening? And in this case, it's going down. If you look at the right side, it's going up. That's what end behavior means. What's happening on the left and the right. Okay, so let's look at the graph of y equals x cubed. Okay, I'm just going to sketch it on the calculator very quick. There's the graph of y equals x cubed. Okay, the way you would describe the behavior, I don't care about the middle section. Okay, that's not end behavior. On the left side, this graph is going down. On the right side, the graph is heading up. And it continues forever up, and it continues forever down. That's how you could write down the end behavior. Down on the left, y is going up on the right. Okay. Any question on that? That's one way to write the end behavior. I'm going to show you one other way. Yep.
Just going to ask if there's another way.
Yes, there's another way. Drawing little arrows and stuff, that's kind of, it's not very, like, mathematical. That's really not the way they would do it, like in a higher level math class. They wouldn't draw arrows. But it's at least a good way to explain it, like, to start, and it makes sense. Down on the left, up on the right. Okay. Once I show you the other way, if the directions don't say which way to do it, I don't care which way you do it. But on the test, you might see a mixture of both. Okay, let me show you the other way. All right, so the other way is like this. And what this says, okay, if I read it exactly the way it's written, and then I'll kind of simplify it, It says the limit of f of x as x approaches infinity. Okay, what does that really mean? Well, f of x really stands for what letter? Y. This basically says what's happening to y as x heads right. So as your x heads to the right, what's happening to your y value? Okay. What's my y value approaching here? Yeah?
Infinity?
It's approaching infinity. What I just wrote right there in words describes what's happening right there. As x heads to the right, what's happening to y? Okay. Let's try this one. This says what's happening to y as x heads left. Negative infinity is left. Okay. So as I head towards negative infinity on the x-axis, as I head left, what's happening to my y value?
It's approaching negative infinity.
It's approaching negative infinity.
So
And that, I'll just do it in a different color. This is describing what's happening right there. Okay, you have two ways, one that's more symbolic, one that's more formal. This definition on the right, this is called limit notation. Okay. And that's a much more formal way than using arrows. Okay, so there's 4 basic types of end behavior. You can either have both ends up, both down, or one of each. Okay, so let's try this one. We just did x cubed. Let's make the exponent 1 higher. Let's do x to the 4th. Hit graph, and I want to identify the end behavior. Okay, so there's my graph. Okay, how would you describe the end behavior of that using arrows? Which one is it?
2 up arrows?
Yeah, it's up on the left, up on the right. Okay, so end behavior, up, up. Let's just describe one part of this with limit notation. Let's do this one. Okay, so what's happening to y as x heads towards infinity, towards the right?
Equals infinity?
Yes. As x heads towards the right, y heads up, which is infinity. Okay. What I just circled the dotted line around, that's that part right there. So that's y equals x to the 4th. Let's do y equals negative x to the 4th. Okay, so when you stick a negative in front, what does that cause your graph to do? Flip. So now, instead of being up, up, now it's going to be down, down. Down, down. Okay, any question on that one? So whether it's up, up, down, down, or one of each, you should be able to tell just by looking at one thing in the graph. So let me go back for 1 second. Let's say you had something like this. There's only one thing there that controls whether it's up, up, down, down, up, down. And that's this right here. All this other stuff doesn't really matter. Okay? Maybe this other stuff would cause little twists and turns, or it might shift the graph or stretch it a little. But if you want to know the end behavior, all you have to really do is look at the number in front and the highest exponent. And it all depends if the number in front is positive or negative, or if the exponent is even or odd. But that's all you need to know.
So would that be down, down?
That would be let's see, that's a cubic, so odd always has one of each. And a negative in front would be the opposite of that. It would be that. So it would be up, down. Up on the left, down on the right. And what I just did is I went through that chart in my head. It was this one. The number in front was less than 0, and the exponent was an odd. So once you know that chart, then you can figure out the end behavior for anything you want. Even exponents are always both up or both down. Odd exponents are always one of each. Okay, to get a little more specific, you're going to look at that number in front. If it's a positive number and it's even, that's like your parabola, basic parabola, up, up. If it's an even exponent and a negative number in front, that would be down, down. Okay. Again, it might do something like this in the middle, but with end behavior, we don't really care about any of the stuff in the middle. All we care about is looking at the ends. Okay. Any questions on the chart? Okay, so this, if I go back to my example that Mina asked me about what the end behavior would be, this negative 4x cubed, that one thing basically predicts what's going to happen. Okay, that's what we call a model. It models what's going to happen. You don't need anything else. So that term, that's called the leading term. And the leading term is what controls everything. Right? It controls everything because it's the highest exponent. Okay, if you compare cubing something to squaring something, there's no comparison. Cubing is way more powerful, if you think of it that way, than squaring. Okay, way, way bigger results. So, if you have some long, complicated polynomial, like 5x to the 4th plus 3x cubed minus 8x squared plus 6x minus 7, I just made something up. Everything I just said, the only thing that matters is the first thing that I said. Nothing else matters. So, if you want to know what the end behavior model for a polynomial is, all you have to do is write down the first term, the one with the highest exponent. That's it. So maybe it's like 3x to the 5th. Okay, whatever it is, you just write it down. Okay, so the last one we'll look at, I think that's example 6 in your notes, is to find what I call it the EBM. Okay, I just call it end behavior model. Okay, what would be the end behavior model of that graph? Josh?
No, it's
Not sure. Ian?
Down, down.
Not the end behavior type. So the end behavior, if we go back to that, just to be clear, end behavior, where is it? End behavior type is the down, down, up, up stuff. The end behavior model, it's an equation. So do you know what it would be there?
Just the first term.
Which is?
Negative 0.5x.
Negative 0.5x to the 4th. That's your end behavior model. Let me, does everybody have what's on the left?
No.
Oops. All right, I'll just put this here for a second then. Let me graph my problem, and then let me graph the end behavior model and show you kind of how they compare. So negative 0.5x to the fourth plus 5x cubed minus 10x plus 1. Okay, so there's the original. And now I'm going to graph just the end behavior model. Negative 0.5x to the fourth. Okay, I just want to see how they look. Okay, there's the original. And coming in red right now is mine. Now, do they look the same? No. Let me zoom. Let me make sure I typed everything in correctly first. Yep, we're good. Let me zoom out. Zoom, 3, and then hit enter. Okay, so there is the graph in blue. There's my graph in red. Okay, it's still, they don't really look that similar. But let me set my y min kind of way down. Let's try like negative 500. There's your blue one. There's your red one. What are you starting to notice about this red line and this blue line? They're starting to get closer together. In fact, the further down that I go, if I go all the way, let's just try like negative 5,000, eventually they're going to look like they're getting very close together, and it's going to look like they're right on top of each other. So there's your blue graph. And there's your red graph. Okay, they're getting closer and closer, and they're starting to look the same. That's the point of the end behavior model. If you zoom out enough, eventually the graph in blue and the graph in red look almost identical. Okay, and if I wanted to make them look even more similar, I could just zoom out a little more. And eventually they would look almost the same. Now the graph in blue does some little twists and turns up here. Okay, it did do some kind of funny things. But big picture, the graph in red and the graph in blue look the same. That's what I'm trying to show you. Or they look very similar. Okay, any questions on that? Any question on the difference between end behavior model and end behavior type? What's type again? Type is the up or down, that's the arrows. And then the model, that's an equation. All right, so the homework tonight's on 161. Okay, it's 1 through 5, 9, 10, 12, 15, 16, 21 to 25, and 29 to 31. Okay, I will be after school for extra help if anybody needs it. And we have our test tomorrow on 2.2 up through 3.2.